So in this particular concept question, we have a ball of mass 2 kilogram and another one of mass 4 kilograms that are dropped together from a 30-meter tall building. It says after a fall of 12 meters each towards the Earth, their respective kinetic energies Ke will be in the ratio of. So here are your answer choices. So I'll go ahead and show you how to do this. Here's the visual for you. Here's M1 being on the left side, which is 2 kilogram. M2 being on the right side, which is 4 kilogram. I've just chosen to go in the order that it was listed. Okay, you can do whatever you want. Here, H being 30 meters, and then the problem says that it has fallen a distance of 12 meters towards the Earth. So my green arrow is going to be pointing downward, and that distance is going to be 12 meters, and the vertical displacement is negative 12. Okay, because it's pointing. Well, displacement is a vector. So depending on how you want to say it. So here, both objects are released from rest, and they have fallen the same amount of distance, which is 12 meters. So in order to do so, I'm just going to set up Ke for the first one. Ke1 equals 1 half m1 v squared. Here, you notice I have m1, but the v does not have a subscript because I know that if both objects, regardless of their mass, when they have fallen the same amount of distance, they should obtain the same speed downward. Okay. So here, VF and these two diagrams are drawn the same size, and they're both pointing down because the displacement is the same. Therefore, G is also the same. So the final velocity is the same for both of them at this particular moment. Well, once I establish that, I can just set up Ke2. Well, Ke2 is just simply 1 half m2 v squared. Once again, this v here does not have a subscript because they are the same for both scenarios. All right. So here, I'm just going to rewrite m2 in terms of m1. m2 being 4 kilograms, m1 being 2 kilograms. So I can just say that m2 is 2 times m1. So if you plug it in, it makes sense. 2 times m1, m1 being 2 kilograms, so 2 times 2 is 4, which is true because it says m2 is 4 kilograms. All right. Other than that, I'm just going to substitute out m2 for m1. So instead of writing m2, I can write m2 as 2m1. Now, why would I want to do that? Because I can make a quick comparison. The kinetic energy 1 on the left side of the screen has m1 in it. So therefore, I can get rid of m2 and introduce m1. It just allows me to make a quick comparison. So here, the 2 that I just substituted in for, I'm actually just going to pull it out to the front. Okay. And I want to keep the 1 half. I'm keeping the 1 half because the function on the left side has a 1 half m1 v squared. So I know that if I keep the 1 half, it'll mirror that eventually. So here, I pull the 2 coefficient inside the parentheses out in the very front, which is there. The 1 half goes there. M1 just gets carried down, and V squared gets carried down as well. But as you can see, on the left side, anytime I see 1 half M1 V squared, which I also locate here, 1 half M1 V squared, I can substitute that statement out for Ke1 because it is Ke1. Right? So 1 half M1 V squared is Ke1. So instead of writing all this junk, I can just substitute that out for Ke1. So here we have Ke2 is 2 times Ke1. So the ratio is a 1 to 2 ratio. So I'm just going to go with B for this one. All right, let's go and crack this one out. This one gives you 4 different masses. Here's A, B, C, and D. Mass A is 1 kilogram, B is 2 kilograms, C is 3 kilograms, and then D is 2 kilograms. And they're all located at different heights above the ground as indicated in the drawing. And we are asked to select correct statements and select all that apply. All right, here for choice A, it says ball A will hit the ground first. I would say that would be a true statement because it has the least amount of distance to travel. So just by using common sense, and I would say that choice A is true. Okay, so I'm going to go ahead and highlight choice A later in just a second. But if you wanted to, you can prove mathematically. Here, I've chosen to write the displacement function for each of these objects, or in general. Vi for all of them is 0, so I'm going to cross that term out. So therefore, delta y is equal to 1 half gt squared. Here, choice A is looking at time. So I'm just going to go ahead and isolate for t by multiplying both sides by 2 and dividing both sides by g. So I'm going to move the 2 from the bottom right to the top left. I'm going to move the g from the top right to the bottom left. Here I have a function for t squared, but really to find t, I would just take a radical on both sides. So I do want to point out that t is y dependent. Well, when delta y is small, which it is in the case of A, when delta y is small, the numerator is small, right? Because 2 times a small number gives you a small number divided by g, and then you're going to square root that, which gives you a small answer. So out of all these scenarios here, A, B, C, and D, the one with the least shortest distance going downward is choice A, which implies that t is going to be smallest which suggests that it gets to the floor first. All right, so I'm going to highlight choice A for that reasoning. B here, I'll do mathematically for you, and then hopefully if you listen to the verbal reasoning afterwards. All right, so it says the potential energy for A is less than potential energy for B, which is less than C, which is less than D. Well, the P function is just MGH here. I can just plug and chug. M being 1, G being 9.8, H being 0.5. So if you do it in your calculator, you get 4.9. And I'm going to do that for B as well. M being 2, G being 9.8, H being 1, you get 19.6 joules. And likewise with C, mass being 3 kilograms, G being 9.8, H here being 1.5 meters, and you should get 44.1 joules. And then last but not least for D, you'll get 39.2 joules. Right? But as you can see already, the potential energy for C is actually greater than the potential energy for D. So why it is located at a less of a height, its mass is actually greater. So the combination of this stuff here gives you an answer that's bigger. So this statement is false because it says potential energy to C is less than D, but it's not. C is actually greater than D. So for that reason, I can cross choice B out. Now, earlier I said you could just use, basic math here. PE has a G in all of them, so really the only thing that matters is M and H. So if you want, you could have just used basic math skill and just compare M and H together, the product of M and H. Well, M being 1, H being 0.5, this is 0.5. Well, 2 times 1 is 2. 3 times 1.5 is 4.5. 2 times 2 is 4. Well, 4.5 is greater than 4, which implies that choice B is already wrong. Okay. Now, let's do choice C. Choice C is super whack because it says the acceleration for A is less than B, which is less than C, which is less than D, which is super, super whack. It says here the air resistance is ignored. So therefore, really, you're falling in the presence of a vacuum. So G is negative 9.8 meters per second squared for all of them. So they cannot be less than or greater than. They all have to be equal. So for that reason, C is wrong. Choice D. Choice D says ball D has the greatest average speed. So this one I think is the trickiest one of them all. So hopefully you're listening well. When an object travels one way, which in this case it is, the magnitude of average velocity is the same as average speed. Okay. The only time the two magnitudes are different is if the object turns around, but it's not. These objects, all 4 objects, are being released from rest, and they're all just falling down. So right away, I can use this particular function. Average velocity is equal to VF plus VI divided by 2. But you notice here I put my statement in parentheses because I'm just looking for average speed, which has no direction. Well, I can cross VI out for all of them because it says that they all are released from rest. So the only thing I have to compare is VF for all of them. I think if you use common sense, you already know that D is right because of the height. Well, if you look at the height, right, this is 0.5, that's 1, 1.5, and 2. The one with the greatest height, it's going to take more time to hit the ground, which allows it more time to accelerate, which implies that V is greatest. So therefore, I know choice D is right, okay, for that reasoning. However, if you don't like the reuse time as your reasoning, you can look at the common form, or this particular kinematics function. VI is 0, so I'm just going to cross VI square term out. So really, VF squared is equal to 2G delta Y, but this off for VF, I can just square root both sides. But here, I've highlighted delta Y for you because, well, you're just multiplying 2 times G times delta Y. So the product of this statement here is greatest when Y is greatest. So therefore, the square root of a large number will give you a larger V. Well, the only object that has the greatest vertical displacement in this case is choice D, being 2 meters off the ground. So it has the greatest speed at the end, or greatest velocity if you want to say downward. So therefore, from that same deduction, I know that V is greatest for choice D. And if V is greatest, the average speed, or in this case, average velocity, will also be greatest. Okay. Alright, so I'm going to go say D is right for that reasoning. Or you can simply use average speed is equal to distance over time. Here, the distance for each one of them is given. This is 0.5 meters. That's 1, that's 1.5, and that's 2 meters. And if you use this function that I derived for expression A, you can actually find the time. And if you really want to do calculator work, you can plug in the distance divided by the time that you would calculate, and it'll validate that choice D is still the correct answer. Okay, so far we have A and D. All right, let's go ahead and crack out E. Well, I already derived a function for final velocity, so watch my cursor, right? This is generic. The final velocity when an object is being released or dropped from rest is just 2g delta y. Here I'm just going to replace it, I'm just going to apply it, except I'm just going to use that function for object A. Well, g stays the same, g is the same, and then here I've chosen to just write delta y A because I'm looking at object A. And object A will now be my reference point, right? You always need a reference point when you make a comparison. So I'm just going to choose object A as my reference point. Here, I'm using the same function again, except I'm just replacing it with the subscript D. So, and then 2 stays the same, G stays the same, and then here is changing Y for object D. But if you look at A and D, right? If you look at A is 0.5 meters off the ground. D is 2 meters off the ground. Well, I would say that D is 4 times the distance. Why? Because 0.5 times 4 is 2. So I can just replace delta y D with 4 times delta y A because it's true. If I take 4 times 0.5, it gets me 2, which is the height of object D. Well, as you can see here, we have a coefficient of 4. Well, the square root of 4 is just 2. So I'm going to pull it outside of the radical sign. Again, the square root of 4 is just 2, so I'm going to pull that out. And then I'm going to keep everything else the same. 2g delta ya stays underneath the radical. But as you can see, which is the same skill I've used before, I'm just going to recognize that radical 2ga, excuse me, radical 2g delta ya is also present here. Okay, here you see the same statement, radical 2g delta ya, and then I can say that radical 2g delta ya is simply the final velocity of object A. So I'm just going to substitute that out quickly. So I have V final for object D is 2 times the final velocity of object A. So here in the statement it says A, VFA is 1/2 VFD. So if I solve for VFA here, I need to divide both sides by 2, which makes it looks like VFD is divided by 2, which is the same as multiplying by 1/2. So I'm going to say that choice E is also correct. Alright, I hope that helps. Stay nerdy, don't be whack.